This video I'm going to talk about something that's covered in real analysis or an advanced calculus class, but we need it for some useful examples and counterexamples in point set topology. So I'm calling this an addendum because I didn't want to take up time in the regular lecture to go through this because I'm not going to test you on it or give you homework problems on it. That'll be in your analysis class. But I do want to use some of these ideas for examples and things in the topology class, and so it'd be good if you could just take some time to watch the video and just kind of follow along. You can scribble some notes along if you'd like to get some better understanding. Alright, so this is about the completeness property of the real numbers, and you'll see what that means when we get to the end. But first of all, to start out, let me give a definition. So let's let S be a subset of the real numbers. Then beta, a real number, is a, and I'm going to put parenthetically the, because it turns out this thing I'm going to define is unique. But I'm not going to prove it's unique. It's not hard to show. It's a least upper bound. So there's what we're defining: the least upper bound for S if two conditions are satisfied. The first one, beta is an upper bound of S. So parenthetically, that's exactly what it sounds like. It means if little s is an element of S, remember S is just a subset of the real numbers. So if little s is a real number inside of S, then S is less than or equal to beta. So beta is an upper bound of S, means that anything in S is less than or equal to beta. And then for it to be the least upper bound, if B is an upper bound of S, then B is less than or equal to beta. Whoops, that's not right. Other way. Let me erase that. Beta is going to be the least upper bound. So if I have another upper bound, B, beta is less than or equal to B. So that's what it means for a number to be the least upper bound for a set. And so that gives us, or it lets us be able to define what's called the least upper bound axiom for the real numbers. Now, depending on what book you're using or what class you have, this axiom may not be stated exactly the way that I'm going to state it. You may get an equivalent form of the axiom depending on how the real numbers are constructed in your analysis or advanced calculus class. But I'm just going to use the one that I think makes the most practical sense for us. So the least upper bound axiom says if S is a subset of the real numbers and S is not the empty set, then S has a least upper bound. And I'm going to go ahead and say that we're going to abbreviate least upper bound with LUB, least upper bound, instead of writing that out every single time. Now this makes an intuitive sense. Any non-empty set in the real numbers should have a least upper bound as long as S has an upper bound. So whenever we have a non-empty set that has an upper bound, it's going to have a least upper bound. Now that doesn't mean every set has a least upper bound, obviously, because some sets don't have upper bounds. The set of real numbers itself doesn't have an upper bound, so it doesn't have a least upper bound. But whenever you have a set, a subset of the reals that has an upper bound, there is a smallest, there is a least upper bound that's going to satisfy the definition on that previous page. Now we can use this to prove the following thing that I'm going to call a lemma, because I'm going to use it in the proof of a couple theorems in just a minute. Now this is one of those things that looks intuitively true. It just makes so much sense. But you know, sometimes obvious things, frequently obvious things in mathematics require proofs. So the lemma just says that the natural numbers, the set of natural numbers is not bounded above in R. Okay, so you see that and you think that is totally obvious. Well, we can actually give a proof of it. So we will prove this lemma by contradiction. That is, we'll assume the opposite of what the lemma states, and then we'll see that something bad happens. So let's suppose n has an upper bound. Okay, well, we can use that least upper bound axiom to say that by the least upper bound axiom, the natural numbers, the set of natural numbers has a least upper bound. So call beta the least upper bound of the natural numbers. But what that means, so for any n, little n, a natural number, n is going to be less than or equal to beta. So here's where things go wrong. But n plus 1 is a natural number. So n plus 1 has to be less than or equal to beta. And n, therefore, will be less than or equal to beta minus 1. But this means beta minus 1 is an upper bound of the natural numbers, and beta minus 1 is less than beta. So this contradicts the fact, or contradicts the assumption, that beta here is the least upper bound. I was able to find another upper bound, beta minus 1, for the natural numbers that is smaller than beta. So that is a contradiction, which means the initial assumption was wrong, which establishes the lemma that n is not bounded above. And so here's the important theorem. that lets us say that the real numbers are complete. If I take two real numbers, call them x and y, and then we'll just assume, without losing any generality or anything, that x is less than y. So take two real numbers where one of them is smaller than the other one. Then there's going to exist a rational number, call it q, a rational number such that q is in the middle between x and y. So any two real numbers you pick, you can always find a rational number that is in between them. So let's go through the proof of this theorem. So proof, since x is less than y, 0 is less than y minus x. By the lemma, one over y minus x is not the least upper bound of the natural numbers. So that means we can choose a natural number, call it m, choose m, a natural number, so that m is bigger than 1 over y minus x. And actually, I think we can say something a little bit, maybe a little bit. I want to phrase this a little bit differently. It's not necessarily that it isn't a least upper bound, but to be a little bit more general, we can say it's not an upper bound. This expression, 1 over y minus x, is not an upper bound for the natural numbers. All right, so that means choose m, a natural number, so that m is bigger than y minus x. Since the natural numbers aren't bounded by 1 over y minus x, I can pick a natural number bigger than them. Okay, and then a little bit of algebra will imply that 1 over m is less than y minus x. So I'm able to find a natural number so that its reciprocal is less than y minus x. So that'll be important. Now, let's let let n be the smallest natural number such that m times x is less than n. Okay. Because the natural numbers aren't bounded, I can always find an n that is bigger than n times x. So I'm going to choose the smallest one. The smallest one that's going to satisfy that. But that's going to mean that n minus 1 is less than or equal to mx minus n. Looking at this expression right here, since mx is less than n, and it's the smallest one that makes that true. If I subtract 1 from it, I'm going to get something that is less than or possibly equal to mx. Now let's divide both sides of this expression by m, and we'll get n over m minus 1 over m is less than or equal to x is less than n over m. And we'll call this inequality, this compound inequality, I'll call that 1. And over here we'll say, since 1 over m is less than y minus x, we're going to get this. So let's see, n over m is going to be less than or equal to x plus 1 over m, which is going to be less than x plus y minus x. Okay, so why is that true? If you look over here at this expression that I called 1, this expression right here. If I had 1 over m to this part right here, I'm just going to have n over m is less than or equal to x plus 1 over m. Okay, but this inequality comes from saying, well, x and x right here, but 1 over m is less than y minus x. So here's my 1 over m, and that is less than y minus x. That's where this chain of inequalities comes from. But just look right here. This says x plus y minus x. That's just y. That's just equal to y. So that gives us, if I'm just going to take, I just want to take the x is less than n over m from right here. So x is less than n over m. And then we'll take that n over m is less than x plus y minus x, or just y. That n over m is less than y. So this is less than y. And that's actually the end of the proof, because look what we found. We started out up here by assuming x was less than y, and we found a rational number. N was a natural number, m is a natural number, so this ratio is a rational number, and it's in between the x and y that were given to us. So that says that in between any two real numbers, we have a rational number. So the last thing I wanted to do was show that it's also true that in between any two real numbers, there's an irrational number. So just to make things a little bit easy on ourselves, I'm going to let s be equal to the real numbers minus the rational numbers. That is, s is just going to be the set of irrational numbers. And so we get a theorem that says, starts out the same as before, let x and y be real numbers with x less than y, then there exists a little s inside of big S with x less than s less than y. So I can always find an irrational number in between any two real numbers that I choose. So the proof of this one is a little bit more straightforward than the last one, I think you'll find. So the proof. So let's take two new numbers that we're going to get from the given x and the given y. So let's take x over the square root of 2, and we'll take y over the square root of 2. Now, why square root of 2? Well, it's just a nice example of an irrational number, and we'll use that fact later. Okay. Now, it's important to note that x over root 2 and y over root 2, they may or they may not be rational or irrational. It just depends on what they are. Okay. Now, but they're definitely real numbers. X over root 2 and y over root 2 are both real numbers. By the previous theorem, there's going to exist a rational number q that is in between the two of them, with x over root 2 less than q less than y over root 2. Now, we can assume that q is not equal to 0. Otherwise, if q was equal to 0, there would exist a q prime irrational number with x over root 2 less than q prime less than q, strictly less than q, important to note, strictly less than q, less than y over the square root of 2. So just assume that q is not 0. Because if, like I said, if it is 0, I can find another rational number that I'll use called q prime, and everything would work the same. So we can assume, without losing any generality, that q is not equal to 0. And then we can proceed from there. So where we're at now is that q is a rational number. It's okay to assume it's not 0, and q is in between x over root 2 and y over root 2. Well, just do what you want to do. Get rid of the fractions. Multiply through by the square root of 2, and you'll get that x is less than the square root of 2 times q is less than y. And then we're done. Since q is a rational number, square root of 2 is not a rational number. That means the square root of 2 times q is not a rational number. That is, square root of 2 times q is an element of what we had called S. So we started out, that's the end of the proof, we started out with two real numbers, x is less than y, and we found an irrational number that lives in between them. So the upshot of this is that in the real numbers, on the real number line, between any two real numbers you can find a rational number, and between any two between any two real numbers you can find an irrational number. So that's what we mean when we say that the real numbers are complete. There are no gaps in them. You can always find rationals and irrationals between any pair of real numbers that you take. And this is going to form the basis of some nice examples and counterexamples that we're going to look at as we finish the point set topology section of the class.